In this series of videos, we will be covering some topics related to image and video processing, particularly image processing, and we will do some topics related to video processing as well as we go along. The first topic that we will discuss in today's video is what is called as the co-occurrence matrix. What is the co-occurrence matrix in terms of images, and how is it useful in image processing, and how do we compute the co-occurrence matrix? Okay, so I'm going to deal specifically today how to calculate the co-occurrence matrix from a given image matrix. As we all know, images are represented as a matrix where the matrix elements represent the brightness levels of the image pixels. Okay, so what is a co-occurrence matrix? A co-occurrence matrix is a matrix that represents how often pairs of pixels with specific values occur in the image at some predefined offset. So we'll see what this means once we see the matrix of an image. So basically, we are going to see the relationship between pixel pairs at a certain predefined offset. So we'll see if a particular combination of pixel values occurs at a particular defined offset value. Okay, so the offset itself can be defined in two different ways. So from a given pixel value, we can define the offset as a pair of numbers, delta x and delta y. So delta x denotes the offset in the horizontal or the x-axis direction, and delta y denotes the offset in the vertical or the y-axis direction. So that's one way of representing or denoting the offset. Another way that is also used sometimes in denoting the offset is in terms of the rows and columns. So the offset can be denoted as a pair of numbers where the first number denotes the row and the second number denotes the column. So the first number represents how many pixels are to be shifted or are to be moved along the direction of the rows, that is in the vertical direction, and the column number represents the offset along the columns, that is horizontally. Okay, we'll see what all these mean with an example, but what is the purpose of doing this? What is the utility of the co-occurrence matrix? A co-occurrence matrix in image processing is useful to analyze the texture in images. So it has applications with analyzing image textures. Okay, so let's dive into the co-occurrence matrix computation. So first, let us look at what do we mean by offset. Okay, so for the given offset values, I'll do an example first for the first representation of the offset in terms of delta x, delta y. So if we have these two numbers as 1, 2, it means the first number represents the offset in the x direction. So horizontally, we move from the reference pixel that many pixels to the right, and the second number denotes the vertical direction movement. So 2 represents going 2 pixels down after having moved 1 pixel right. Okay, so let's look at this particular image pixels where I marked this pixel in pink. So with reference to this pixel, what is the offset pixel which is at an offset of 1, 2, where 1 and 2 represent the delta x and delta y parameters. So delta x denotes the number of pixels that we move in the horizontal direction to the right. So that means from the reference pixel, we will move 1 pixel to the right. So we go 1 pixel to the right. So that's our 1 pixel right, and then after having moved 1 pixel right, from there we have to move 2 pixels down. So we move 1 pixel down here and another pixel down here. So we have the first pixel down and the second pixel down. So that means the pixel which is having an offset of 1, 2 from this reference pixel in the pink shade is this particular pixel here. So let's shade that with the same pink as well. So that's the pixel of interest. So this is the pixel that is having the same offset as described by the offset parameters 1, 2 with reference to the pixel shaded in pink. So let's mark that. So I'm going to shade that as well. So that's our pink pixel which has an offset of 1,2 from the given pixel, which is this one. Okay, similarly for this pixel which is shaded in green, the pixel which has an offset of 1,2 is we have to move one pixel to the right. It's one right and two down, so we move one to the right and 2 pixels down, so we come here. So we have this as our offset pixel. So the corresponding offset pixel to the green is this pixel over here. Okay, so this is the meaning of offset, and what we want to look or calculate in the co-occurrence matrix is, for this particular offset we want to count how many times a particular value of pixels repeat themselves with this given offset. So we'll see how to do that. Let us first understand offset here, and we'll see how to calculate the co-occurrence matrix in the next slide. Okay, so that's one way of representing the offset, using delta x and delta y, where the delta x denotes the offset in the x direction and delta y denotes the offset in the y direction. So x direction is horizontal and y direction is vertical. But sometimes we can also use the offset description in terms of rows and columns. So if it is rows, let's see, for example, an offset of 2,2 in terms of row and column, then for a given reference pixel, the other pixel which will be at this offset of 2,2 will be 2 rows down. So from here we have to go 2 rows, so that's one row and that's the second row. So we are moving along the row direction. Remember, rows are these horizontal boxes, so each line horizontally represents a row. So that's row number 1, row number 2, row number 3, row number 4, and row number 5. So the first parameter represents the offset along the rows. So we go from the row 1 to row 2, that's one offset, and row 2 to row 3, that's 2 offsets. So the number is 2 here. So we shift 2 rows down. So we have come to this pixel here. So let me mark the arrows. So that's 2 rows down. And then we have the second parameter is also 2. That means that's the column offset. So from here we have to move 2 columns offset. So from here, that's one column offset, and that's the second column offset. Okay, so again, the columns, we have these vertical elements. These are the columns. So that's the first column, that's the second column, that's the third column. So the column offset, we move from one column to the next column. So the offset of the columns is 2. So we move from the first column to the second column, that's one offset, and from the second to the third column, that gives us the second offset. So after having moved 2 rows down and 2 columns right, we arrive at this particular pixel. So the pixel which is at an offset of 2,2 from the reference pixel is this particular pixel. So we'll shade it with the same color. So this will be our pixel which is having the same offset as our reference pixel. Okay. Similarly, for the pixel which is shaded in orange, the corresponding pixel at the offset of 2,2 is we have to go 2 rows down and 2 columns to the right. So we go 2 rows down. So the first row down will bring us here, the second row down will bring us here, and I'll mark the arrows as well. So the first row down is here, the second row down is here. So we arrive at this particular pixel, and then we have to move 2 columns to the right. So that will be one column to the right here and another column to the right here. So again, we'll mark the arrowheads. So that's our arrowhead here. So corresponding to the orange pixel, the pixel which is at an offset of 2,2 is this particular pixel. Okay, so I'll mark it with the same color. So this is what we mean by offset, and it depends on how we denote it. In some authors or some people prefer to denote the offset in terms of the row and column, and some people prefer to denote the offset in terms of the x and y offsets. Okay, the offset along the x direction and y direction, and in some cases it is along the rows and columns. So this is an example for rows and columns. So for this yellow pixel here, or the orange pixel here, we go down 2 rows and we move 2 columns to the right, so we arrive at this pixel. So what we basically see is that for the given offset, we get the relationship between the positions of the pixels. Okay, so the offset basically gives us a relative position between the 2 pixels. So we have, in this particular case, this is the relative position of the 2 pixels, and in this way we can keep finding the relative pixel for each of the pixels based on this particular offset. So for example, for this particular pixel, the other pixel which will have the same offset is this one. Okay, so based on this, we will have a relative position of the pixels with reference to a given pixel in the image. Now once we understand what is the offset, what we are trying to do next is, in the co-occurrence matrix, we want to find how many times a particular pair of pixel combinations occurs in that particular offset relationship. Okay, and let's see how to do that in the next slide. Okay, so basically we have an image matrix, and the image matrix contains these numbers which are representing the brightness levels in the image. Now I've used something very simple here, where we have used only 4 different brightness levels. The 4 levels are 0, 1, 2 and 3. So those are the 4 different levels. That means each pixel is having one of the 4 brightness levels. The brightness level can be either 0 or 1 or 2 or 3. So one of the 4 brightness levels. In practice, actually, the number of brightness levels is going to be much higher, and especially when you have color images, we will have a lot of brightness levels corresponding to the colors. But for simplicity, we are just going to consider an image which consists of only 4 different brightness levels. That means each pixel will have a brightness level of either 0 or 1 or 2 or 3, as we have seen in this. And I have given some brightness levels to each of these pixel cells in the image. Now, the co-occurrence matrix that we will produce will have a certain dimension, which is S by S, where S is the number of brightness levels. So for our example here, the number of brightness levels that we are using is 4. So there are 4 brightness levels, which is 0, 1, 2 and 3. So therefore our co-occurrence matrix will be a 4 by 4 matrix. So we have 4 rows and 4 columns. So the co-occurrence matrix is going to be 4 by 4. So the dimension of the co-occurrence matrix depends on the number of different brightness levels that are present in the image for which we are computing the co-occurrence matrix. So since in this case we have 4 different brightness levels, the co-occurrence matrix will be a 4 by 4 matrix, which I have highlighted in red here. Okay, the additional cells which I have here are for representing the pixel values. So the 4 pixel values that we can have in our image are 0, 1, 2 and 3. So for computing the co-occurrence matrix, we will write those pixel values in these cells here. So we'll write 0, 1, 2, 3, and similarly here we will write 0, 1, 2, 3. Okay, so those are the 4 different pixel values that are present in our image. And what we are going to do now is we are going to count how often that particular combination, for example, for this cell or for this particular box here, we have 0 along the row and 0 along the column. So we are going to look for pixel pairs which have 0 and 0 in the predefined offset. So the offset given here is 1, 2 in terms of delta x, delta y. So that means 1 pixel right and 2 pixels down. So if we start from the first pixel and go 1 pixel right and 2 pixels down, it comes here. So the offset of interest is going to be let's say so I'm just going to mark for one of the pixel pairs, and we'll have to apply the same relationship, offset relationship, for all the pixels. So we have 1 pixel right and 2 pixels down, it brings us here. So from the given pixel, if we move 1 pixel right, it comes here, and when we go 2 pixels down from there, we come here. So the relative pixel at that offset from the first pixel is this particular pixel here. So we have to check now how many times 0 and 0 occur in that relative positions. Okay, so for 0 here we have a 3 here, so it's not 0 0. So we want to count how many times 0 and 0 occur in that relative position. So now if we look from here, so we want to look for each of the zeros, for the first element 0, and we will look at that particular offset and count if there is another 0 in that position. So I have a 0 here, and at the offset it is not a 0, so we will not count that. I have a 0 here, so from the 0 at the defined offset we have to go 1 right and 2 down. We come here, this is not 0. If this was 0, we will count that as we will increment the count for the 0 0 combination. So this is 0 2, so we can't include anything here. This is a 0 here. From here, if we go to the offset, we go outside the image, so there is nothing there. Corresponding to this 0, we can go 1 step to the right, but when we go 2 steps down, we go outside the bounds of the image. So again, there is no 0 0 pair there for the defined offset. And again for this, if we go for the defined offset, it takes us beyond the bounds of the offset. So that means for the defined offset pixels, or the defined offset relationship, there are no pixels which have 0 and 0 as their values. So the number of times the 0 0 pair occurs at that predefined offset is 0, so we will write it as 0. Okay, so similarly we do it for the other combinations. Let's say for the second box here, the first pixel is 0 and the second pixel is 1, so we have to look for 0 1 combinations at that particular offset. So for the 0 here, we don't have a 1 here, so we can't count that. For this 0 here, it's not a 1 here, so that's the offset pixel. For this 0 here, it takes us outside the bounds of the image, and for this 0 here, it again takes us outside the bounds of the image. So 0 1 combination of pixels do not occur even a single time in that defined offset. So therefore the number of times we get 0 and 1 as the pairs of pixels in that defined offset is also 0. Now if we look at 0 and 2, so this box corresponds to the pixel pairs having values pixel 0 and pixel 2 for that offset. So if we have the 0 at the offset, we don't have a 2, so it's a 3 here. But for this pixel now, 0, at the predefined offset, which is 1 step to the right and 2 steps down, we have a 2. So 0 2 occurs 1 time. Similarly, let's see if there is a 0 2 combination occurring at that offset in any other location of the image. So for this, it takes us outside the image, so we can't do that. For this also, it takes us outside the image, it doesn't matter. And here also it goes outside the bounds of the image. So therefore 0 2 occurs only 1 time. So we have a 0, and at the offset we have 2. So 0 2 occurs 1 time in the image, so we'll write it as 1. So the number of times that particular pixel pairs values occurs at that particular defined offset is what we are computing in the co-occurrence matrix. Next, moving on to this particular cell, which is looking for the combination of pixel 0 and pixel 3. Pixel value 0 and pixel value being 3. So 0 3, so we have this first particular element. So at the defined offset we have 0 and 3, so that's 1 time. At this particular 0, it's a 2, so we don't count it. These two zeros take us outside the bounds of the image, so there is nothing there. So therefore the number of times we have 0 and 3 as the pixel values at the defined offset is once again 1. So we will just put it as 1. So similarly we keep going on doing this. Now for this particular cell, we are looking for a combination of 1 and 0, 1 0 pixel values at the defined offset. So we are going to look for 1, and at the defined offset we have to look if there is another 0. So for this particular one, at the offset it's a 1 and not a 0, so we can't count here for 1 0. This takes us outside the image. For this particular pixel here, it's a 1, and at the defined offset we have a 0. So 1 0 occurs once. Is there any other one here? From here it's a 1 and it's a 2 here. So therefore 1 0 occurs only one time, which is in this particular offset. Okay, so here and here we have 1 0, and it's only one time in the image that we see a combination of the pixels having the pixel value 1 and 0 at that particular defined offset of 1, 2. So we say it's one time. Now let's look at the combination for 1 and 1. So at a defined pixel value, so for this pixel we have a 1, and at the offset it's also a 1. Okay, so the offset is 1 right and 2 down, so it's a 1. So 1 and 1 occur one time here. Let's see if there's any other 1 and 1. So for this one it will take us outside the image. For this one it's a 0. For this one it's a 2. For this one it will go outside. For this one it will also go outside. So we have 1 and 1 occurring once. So this is the one time where the two pixels have pixel values 1 and 1 at this defined offset of 1 right and 2 down. Okay, so the number of times we have 1 and 1 as the pixel values is 1. Let's look at the combination of 1 and 2, pixel value being 1 and then the offset pixel being having a pixel brightness value of 2. So for this, the offset pixel is this, it's 1 and 1. For this it's outside the image. For this it's a 0, and for this it's a 2. So if you go from this pixel value, which is 1, we are looking for an offset of 1 right and 2 down, and we have a 2. So 1 and 2 occur in that offset, and there is only one time that we see such a thing. So the number of times we have 1 and 2 as pixel values at the defined offset is also 1. Similarly, now let's search for the pixel combinations having brightness values 1 and 3 at the defined offset. So again, for 1 it's a 1. For 1 it is outside. For this one it is 0. For this one it's 2, and for this one it takes us outside the image, and for this one it takes us outside the image. So therefore 1 and 3 do not occur in the image in this defined offset. Okay, so the number of times we have pixel brightness values occurring as brightness value 1 and 3 in the defined offset is 0. So we put that 0 here. Okay, next we are looking for the combination of pixels having values 2 and 0 in the defined offset. So we are searching for 2 first. So we have a 2 here. From this 2, if we go 1 right and 2 down, we see if it is 0. If it is 2 0, then we will count that, otherwise we will not count that. So here we have 2 and 3. This 2 will take us outside the image. This 2, if we go to the offset, we get a 2. This 2 goes outside the image, and this 2 also outside the image. This 2 also outside the image. This 2 also outside the image. So 2 0 does not occur even once in the image in the defined offset. So therefore the number of times we get 2 and 0 pixel values at that offset is 0. How about 2 and 1? So we'll search through the pixel values which have 2. So that's a 2, and at the defined offset, if you go 1 right and 2 down, we get a 1 here. So that's 2 and that's 1 at the defined offset. So 2 and 1 occurs once. For this 2, let's see at the offset what we get. It's a 3, so it's not 2 and 1. And for this 2, it's a 2. And for these 2's take us outside the bounds of the image, so we don't need to worry about them. Okay, so 2 and 1 occurs one time. How about 2 and 2? So again, we are going to look for pixel values which are 2, and then at the offset we will look if there is a 2 and 2. It's not a 2 and 2 here. For this, it's not a 2 and 2. For this pixel we have 2, and if we go 1 right and 2 down, we have a 2 here. So at the offset we have pixel value 2 and 2. That's one time. And is there any other place where we get 2 and 2 at the defined offset? Nowhere else. Okay, so the 2 and 2 combination occurs at the defined offset only once in the image, so we put again here 1. Similarly 2 and 3. Okay, if you look at the pixel combinations of 2 and 3 at the defined offset, so for the pixel number 2, pixel value 2, this particular pixel at the offset it's 1. For this pixel at the defined offset it's 1 right, 2 down, so we have 3. So 2 and 3 occurs once. Is there any other place where you have 2 and 3? This is 2 and 2. These are all going to take us outside the bounds of the image. So 2 and 3 occurs once, so that's 2 and 3, that's that 2 and that 3. Okay, so it occurs only one time in the image, so we put 1 here. Now let's look at the combination of pixel values 3 and 0. So 3, 0 at the defined offset. So we have a 3 here, and at the defined offset we go 1 right and 2 down. It's not a 0, so we can't count that. For this 3, we go 1 right, 2 down. It's not a 0. For this 3, we go 1 right, 2 down. It's not a 0. For this 3, we go 1 right and 2 down. It is a 0. So 3, 0 occurs once. And is there any other instance where we get 3 and 0 in the defined offset? Nowhere else. This will take us outside the image. All these will take us outside the image. So therefore 3 and 0 occur in that offset one time in the image. So 3, 0 is one time. How about 3 and 1? So for this particular 3 at the offset we have 3. For this particular 3 at the offset we have 2. For this particular 3 we have 3 at the offset. For this 3, it's a 0 at the offset, and that's it. All the others will take us outside the bounds of the image. So 3 and 1 does not occur even once in the image. So we'll have to put that value as 0. Okay, so 3, 1 does not occur in that offset in that particular image. Okay. Next, we want to look for the combination of pixel values having values 3 and 2 in the defined offset. So for the defined offset, if we start from this 3, at the defined offset is 3. For this 3, at the defined offset it's 2. Okay, so we have one count here. So 3 and 2 occurs once. Anywhere else? 3 and 3, 3 and 0. All the others will take us outside the image. So 3 and 2 occurs once in the image at the defined offset, so it is 1. Okay, so next let's look at 3 and 3. So for this 3, if we go by the offset, 1 right and 2 down, we have 3 and 3 here. Okay, so that's once. For this particular 3, at the offset 1 right, 2 down, it's a 2. So we are looking for 3 and 3. So no, not here. For this particular 3, if we go 1 right and 2 down, that's a 3. So that's the second time we are getting that 3, 3 combination at the defined offset. So the first time was here between these two, here and here, and now the second time it's here and here. So that's the number of times we have the 3 and 3 combination is 2 so far. So for this 3 at the offset it's a 0, so we don't count that, and the other 3s will take us outside the bounds of the image, so we don't count. So there are 2 times that we get the pixel values having the values 3 and 3 at that particular defined offset. So we'll put the number 2 over here. Okay, so because we get 3, 3, pixel value 3 and pixel value 3 at the defined offset twice in the image, so that's once. So I'm going to mark this 3 and 3. So we have a 3 and 3, that's once, and we have this 3 and this 3, that's twice. Okay, so that's why we have put 2 in this box. Okay, so basically we have to look for the pixel pair values that we see in this matrix and count the number of times that that particular pixel pair values occur at the given offset. Okay, so the offset matters because we are looking for the pixel values occurring in that spatial relationship within the image. So basically the offset is telling us the spatial relationship between those pixels. So this is the spatial relationship between these two pixels. At that spatial relationship, we want to count how many times we get different combinations of pixels. How many times do we get 0 and 0 in the image in that spatial relationship? How many times we get 3 and 3 in the image in that spatial relationship? How many times we get 1 and 1 in that spatial relationship? How many times we get 2 and 1 in the image in that given spatial relationship, and so on. And that is what is being computed in the co-occurrence matrix. So once we compute the co-occurrence matrix, this is used in image processing to analyze the texture of the images. Okay, so we have seen in this video what is a co-occurrence matrix and how to compute the co-occurrence matrix based on the spatial relationship between the pixel positions. So again, the spatial relationship can be defined in two different ways. So you have to be careful what is the spatial relationship given to you, whether it is given in terms of delta x, delta y, or whether it is given in terms of the row and column numbers. So accordingly, you have to find the spatial relationship, and based on that, you can calculate the co-occurrence matrix.